Topic 2, Mathematical Programming, Part 4, Sufficient Conditions for an Optimal Solution. So this is a slightly more advanced section, and it also highlights things that can possibly start to cause some complexity in mathematical programming. And the thing that comes out of this is that perhaps are some types of functions that you should avoid. And so as a result of that, there's a set of functions which actually tend to be much more amenable to finding optimal solutions than others. So to explore this, I've found this horror function here, which is just called fun, somewhat ironically. It's a pretty complicated function. It's got polynomials in there, it's got exponential to the power of polynomials. I wouldn't fancy taking the derivative of that. I suppose Mathematica would do it very easily, but I wouldn't fancy taking the derivative of that but by hand. So quite a complicated function. If you then try and analyze this function in the usual way, then you take the partial derivatives of fun with respect to x1 and fun with respect to x2, and you set those equal to 0, and you let Mathematica do that because you wouldn't fancy doing it yourself because it would take quite a long time. Probably would take me about an hour to solve this if I didn't have Mathematica at hand. Then actually you get, for this function, you get 5 stationary points, and that's without having any constraints. And the stationary points are listed there, and we put them into a matrix there so that we can use them later. Okay, so that's a nasty function, lots of stationary points. So then the question is, what's the nature of these stationary points? Are they maxima? Are they minimum points, minima, or are they saddle points, which we've mentioned but we haven't really analysed in any detail? So the obvious thing to do is to plot these, and we could start off doing a contour plot, and the function's got this quite elegant shape here, and these points here have identified the 5 stationary points. So there's one there, one there, one there, one there, and one there. We could probably label these contours, and that would tell us something about the stationary points, or we can complement the contour graph with a 3D plot over a sense of a range of sensible values here. So we've identified the stationary points as red dots here. So we can now see that these stationary points, so if we go back to the labeling here to just make sure I get it right, then that's point A, that's point B down there, point C there, and then we've got D and E. So from the diagram, we've got B is a minimum, D and E are, sorry, I should have said B is a local minimum. D and E are local maxima, and they actually have got the same objective function value, so there's a tie there for which is the best point. And then A and C are these they're these saddle points. So we're familiar with maxima and minima from previous discussions, but these saddle points are less familiar. So well, the nature of a saddle point, I mean, it looks like the shape that a saddle makes on a horse's back, and so you're going up to the head and you're going up to the tail, but then the actual saddle's at a low point on the horse's back. So when you look at a saddle point, then in this direction, it's a bit like a maxima in that you're going up and then you're coming. If I go in this direction, then you're going up and then you're coming down. But then in this direction, then you're coming down and going back up a ridge. And this point is identical, going up and then going down. But when you look at it this way, then you're actually going up there and you're going up there. So these are saddle points. When you take the partial derivatives at that point, they are actually stationary points because the two partial derivatives are equal to 0 there. Okay, so we've now identified the 5 points in this diagram. What does it look like if we want to do this analytically? Well, things get worse, really. We define a thing called a Hessian, and the Hessian we've sort of encountered before with the sufficiency conditions, but we're going to use it in a more of a sort of recipe book type way. So the Hessian, what it does is we have to take the second partial derivatives for x1, the second partial derivatives for x2, and the cross partial derivatives. That's derivative of x1 with respect to x2 and x2 with respect to x1, and these two are symmetrical. They're always the same. And so we get this function, very complicated function here, which you don't need to worry about. Now there's some recipe book rules. So if this is the Hessian here, where we're representing the partial derivatives by a's, then we get a11, a22, a21, a12, and for a minima, if a11 is greater than 0 and a11, a22 minus a21, a12 is greater than 0, the point is a minima. If it's a maxima, then the signs alternate. The first one is negative and the second one is positive. And if it's a saddle point, if this is it's neither of the two conditions above. So if we then go through all the stationary points and work these out, so we work the names of those conditions are first principal minor and second principal minor. But you'll see what they are up there. Then you'll see that point A is identified as a saddle point because both the first term and the second term are negative. For it to be a maximum, then this term would have to be positive. Point B is identified as a minimum because both of these are positive. Point C is identified as another saddle point. In fact, it's identical to the first one because these both are negative, and then D and E are identified as maximums. So this can get very, very complicated, but the main message to get from this is, well, first, something a bit more rigorous about sufficiency conditions and using the Hessian matrix, which once you set it up is actually pretty straightforward to do. But the other thing is to identify how complex functions can be, and that it's actually a good idea to think carefully about the functions that are chosen in a mathematical programming model, and that's the topic of the next recording.